Hi guys, it's Mrs. Seitz. Today what you're going to be working on is lesson 5.1, which is perpendiculars and their bisectors. So the first part of your lesson is going to focus on perpendicular bisectors. So the overall objective of the lesson is to use properties of perpendicular and angular bisectors. So for the first part of the lesson, we're going to concentrate on perpendicular bisectors. And a new perpendicular bisector theorem is the first focus. And it states if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of a segment. And so here's how this works. If you have line CP and it is the perpendicular bisector, which remember, perpendicular bisector means that bisect means to cut in half, and perpendicular means that it cuts in half at a right angle. So here's line CP, and it's the perpendicular bisector of line AB or segment AB. So meaning that it's cutting AB into two equal parts. And you can see that with the indications that are on the picture. And you can also see that it's cutting at a right angle because it has a 90-degree mark. Okay, then here's what that perpendicular bisector theorem says. Then the other two segments that you see, so segment CA, so it's almost forming a triangle here. So CA is equal to CB. And I'm going to mark my tick marks on here too. So CA is equal to CB. All right, and then the opposite is also true, the converse of the perpendicular bisector theorem. So it says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So for example, if we're looking at the triangle that's down at the bottom, so triangle ADB, and we know that DA is equal to DB, then what we can say is that D would be lying on the perpendicular bisector of AB. So again, to make sure you're looking at that, if we know that AD or DA is equal to DB, so if we have the opposite, then we can say that point D was lying on the perpendicular bisector of AB. So it's the flip-flop of the one that we just talked about. Okay, so we're going to put that perpendicular bisector theorem now to use. So let's take a look at the first example. So in the diagram shown, ray BE is the perpendicular bisector of segment AC. So let's take a look and see what we have. So here's ray BE, and they're telling us that it is the perpendicular bisector of segment AC. So here's segment AC. So what segment lengths have to be equal? Well, in part A, we have to know by definition, right, that by a perpendicular bisector cuts things into equal parts, right? So we would have to know that AE has to equal CE by definition of a perpendicular bisector, right? So we're going to write that down. AE is equal to CE, and that's by definition of a perpendicular bisector. Okay, but we also know by the perpendicular bisector theorem, which is our new one, that if we know that we have a perpendicular bisector and we have these connecting lengths from the perpendicular bisector down, so AB and CB, and we know that they fall on that perpendicular bisector, then we can also say that AB is equal to CB. Because point B is a point that's on the perpendicular bisector. I'm going to write that down. So that means then it would qualify for the perpendicular bisector theorem. Okay, so now let's take a look at part B. Part B says AP is congruent to segment CP. What can you conclude about point P? All right, so here's another fact they're saying. If we know that segment AP is congruent to segment CP, well, we can now say something special about point P. And here's that fact that we can say. We can say that point P is on the perpendicular bisector of segment AC. Okay, and how do I know that? Well, the reason goes back to the converse of the perpendicular bisector theorem. Okay, if you know you have two segments that are equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. So it meets that qualifications for that converse, and I'm going to write that down. Converse of perpendicular bisector theorem. Okay, so that's the meeting the qualifications for that. It's for part B. The next two blanks that you have there, we're going to be putting some phrases in there. Some of it might be a little bit review, but it's good to go over some of this as we get into some of the definitions a little bit further. So the first phrase that we're going to be filling in the blank is the distance from a point to a line is defined as the length of a perpendicular segment from the point to the line. So it says, for instance, in the diagram shown, the distance between point Q and the line M is QP. Okay, so this length here of QP would be that distance. And notice how we don't have that segment symbol above it when we talk about a distance. Okay, when a point is the same distance from one line as it is from another line, then the point is, and we say the phrase, equidistant from the two lines or rays from the segment. Okay, so when the point is the same distance from one line as it is to another line, then we say the point is equidistant from the two lines. And it was important for us to talk about those things because now we're going to be talking about the other part of today's lesson, which is about angle bisectors. Okay, and if you take a look at Theorem 5.3, Theorem 5.3 is all about angle bisectors, and it states, if a point is on a bisector of an angle, then it is equidistant from the two sides of the angle. So if we have that the measurement of angle BAD, so I'm going to mark that, so BAD is right here, is equal to the measurement of angle CAD, so this arc mark down here at the bottom, then what we can say is at the top that DB is equal to DC. Okay, and again, I'll say that one more time. If a point is on the bisector of an angle, so we have point D being on that angle bisector, right? Then it is equidistant from the two sides of the angle. So we have BAD being equal to the measurement of angle CAD. So therefore we can say that BD is equal to DC. And we also have its flip-flop down here. If a point is in the interior of the angle and is equidistant from the sides of the angle, okay, so we're still looking at point D and we're going to the sides of the angle, then it lies on the bisector of the angle. Okay, so we got the flip-flop. So this time we have, if we have DB is equal to DC. So this time we're starting with the sides. Then we can say that the two angles were congruent. So we can say that the measurement of angle BAD is congruent to the measurement of angle CAD down at the bottom. Okay, we're going to put this to use now by taking a look at this baseball problem. All right, so we're going to be using some angle bisectors, and actually we're going to be drawing a little line here to help us out too. So we're going to use this diagram of a baseball infield shown at the right, and we're going to figure out what we can conclude about the measurement of angle SHF. Okay, so before we do that, we better actually draw a line through there. So I'm going to draw a line as best as I can through home plate, through the pitcher's mound, and to second base. I want you guys to do the same. Okay, so one thing I want you guys to notice is about point S. Okay, and one thing I want you to notice is that point S is in the interior of the angles, okay, that I've just created. And if you look at the angle I'm talking about angle SHF, and I'm talking about angle SHT. So I'm looking at these guys. So here's angle SHF. So I'm going to outline that in blue for you. And then I'm going to look at angle S, H, and T. And I'm going to look at that in green. Okay. All right, this is actually a nice application of the angle bisector theorem. Okay, one thing I know, and I think you guys might know this about baseball too, it's the same distance to get from first base to second base as it is to get from second base to third base. And it's actually marked here in the picture. So if you know that fact, that's equal distance to get from second base to first base as it is to get from second base to third base, then this is actually an application of the converse of the angle bisector theorem. So I'm going to write that down. Let's write that down on our answer page. So converse of angle bisector theorem. Because we know that those two sides have to be congruent, then we know that that this point S lies on the angle bisector, okay? So we can say point S lies on the bisector of the angle. So here's what we can say now. We can say that we know that the measurement of angle SHF has to be equal to the measurement of angle SHT. And what do we know about it? Well, hey, look, it's 90 degrees, right? So guess what? If we know that they both have to add up to 90 degrees, right? What's 90 divided by 2? 90 divided by 2 is what? 45? So that means they both have to be equal to 45 degrees. So the measurement of angle SHF has to equal 45 degrees. Okay? So again, that's a nice application of the converse of the angle bisector theorem, because we know from second base to first base and from second base to third base, it's equal distance. So we can say that it's a straight shot from second base to home plate, right? So we can say that it's an application of the converse of the angle bisector theorem, because second base, or point S, lies on that angle bisector. And so we can say we got a 45-degree angle at angle SHF because we know it's a 90-degree at home plate, so we're cutting it in half. I know there was another problem in front of this one, but I want you guys to skip right now to the second checkpoint question, because we've been talking about the angle bisector theorem, and I want us to keep going with that, okay? So let's take a look at it. In this diagram, D is on the bisector of angle ABC. So I'm going to draw that angle bisector right now. I want you guys to do the same. And the first question is asking you, what is DC? Okay, well, if we know that this is an angle bisector, then one of the statements in the angle bisector theorem is saying that the distance from AD to the angle bisector is equal distance, right? So AD and CD would have to be equal lengths. So DC would have to equal 6 as well. And the reason for that is because these guys are equal as well. The angle's down at the bottom because we have an angle bisector. So we're going to say because the measurement of angle ABD is equal to the measurement of angle CBD, then we can say AD is equal to CD, and that's because of the angle bisector theorem. And again, this is the angles we're talking about. So these guys down here at the bottom are equal to one another. Because the angles down at the bottom are equal, then we can say that those lengths are congruent as well. All right, one more question, and then we're done with today's lesson. And it is an application of a perpendicular bisector theorem. Okay, in this one, it says in the diagram, PQ is congruent to RQ. So I'm going to mark my tick marks. Okay, what conclusion can you make about point Q? Okay, so let's think back to the perpendicular bisector theorem. If we know that we have those two lengths that are equidistant, then we can say that point Q has to be on the perpendicular bisector of segment PR. Okay, and that's an application of the perpendicular bisector theorem. So that answers our first question. All right, the second question says, can you conclude that point S is also on the perpendicular bisector of PR? Okay, now we need something actually to be congruent for us to be able to say that S is on the perpendicular bisector of PR. And here's that thing that we need to be congruent. We need to say that PS would have to be congruent to RS. And that information is actually not given to us in the problem. So because we don't have that information given to us, we don't know that that would have to be on the bisector. So because of that, we don't know that S would be on the perpendicular bisector. So we're going to say no, because we don't know if PS is equal to RS. We cannot conclude that S is on the perpendicular bisector of PR. Okay, so again, there were two main important concepts from today's lesson. One was the angle bisector theorem, which said if you have a point that's on the bisector of the sides and it's equidistant from the two sides of the angle. So if you know that you have a point that's on the bisector, so you know you have that if the two angles are congruent, then you can say that the two sides that you have from that point are equidistant. Okay, the other one that we had that was important today was the perpendicular bisector theorem. And what that said is if you have a point that's on the perpendicular bisector, then you can say that the lengths that were equidistant from that point to the endpoints would be equal to one another. All right, we're going to keep practicing that today in today's class. Let me know if you have any questions.